Okay, first question. And if you don't get these, even if you do get them, you might want to write down these answers. If you don't have them, I'll zoom in a bit on them so you can see them a little better. First of all, which of the following questions our equations is correctly written? First one, it's delta E. It's the E value for the products minus E value for the reactants. Why is it A and say not B? Most of you have it right, but why is it A and not B?
E final.
Final minus initial. Final minus initial. So if you're in a chemical reaction, which state is the final state? Products. And the initial state would be the reactants. All right? So that's the thing to remember. If you don't remember it's products minus reactants, think back to what the delta symbol means. It means to take the final state minus the initial state. Okay, next up, in an endothermic process, which of these is true? And we found out on Tuesday that delta E must be greater than 0. We said that it has to be positive, which of course is the same as saying is it must be greater than 0. Next up, in an exothermic process, one which we are giving off energy to the surroundings, delta E then must be less than 0. In other words, it must be negative. Again, if you don't get these, write them down. Next up, when the system gains heat, then the Q value, Q must be greater than 0, which means that the Q value must be positive. And, did I skip one? No, I didn't. All right. When work is done by the system, then the Q value must be less than 0. So it looks like we need to review this one. Let's go back to where we ended the class on Tuesday. When we ended the class on Tuesday, we talked about these sign conventions. And when we talked about these sign conventions, we said that when work is done by the system, then the value of W is negative. And so if we go back to our syringe, that's the example we used. If I were to hold this end of the syringe so no air can get out, tell me which direction the system is doing work. Is the system doing work now when I'm pressing down? Or is the system doing work now when I'm letting go? When I'm pushing down, is the system doing work? Or is the system doing work now?
No.
Right now, exactly. The system is doing work because whatever pressure is in there is pushing that plunger back up. So in that case, the system is doing work. And when the system is doing work, then again the sign is negative. And that's because when we look at the volume, that final volume is greater there at the end than the initial one. That actually wouldn't make sense in this. So that's going to be actually something that we have to talk about on the sign conventions later on. But again, the system does work, the sign is negative. All right, next up here. What is the relationship between the internal energy of the system and the internal energy of the surroundings in a chemical reaction? And this one here, as we said, that the signs must be the opposite of each other. If the system does work, then that means that the surroundings has work done on it. Or if there's energy released by the system, that must mean it's gained by the surroundings. Therefore, the signs must be opposite. This one here relates the heat of the system to the heat of the surroundings. Again, the signs must be opposite. Whatever happens to the system must be just the opposite what happens to the surroundings. So again, delta E has different signs, system and surroundings. Q has different signs, system and surroundings. So I bet that means we know what the next one should be here. If we talk about the work of the system and the work of the surroundings, then the signs must be opposite once again. So again, whatever work is done by the system must have been done on the surroundings, and vice versa. The signs are opposite. Any questions on these? Any questions? All right, so that takes us back again to where we ended on Tuesday. It's important that we know these sign conventions. We don't want to have to flip a coin. Again, you and I are always a part of the surroundings, and we're always trying to make a judgment as to what happens to the system. And whatever happens to us in the surroundings is just the opposite of what happens to the system. So again, as part of the surroundings, it's just the opposite. That's why the signs are the opposite: system and surroundings. We have a relationship here that we're going to look at today that says Q is equal to C delta T. Now what these stand for is this. We already looked at Q. Q stands for heat. Delta T is not change in time, but change in temperature. And then C, this is a capital C, this here stands for the heat capacity. C is the heat capacity. And we define the heat capacity like this. We say that the heat capacity C is defined as being the heat required to raise the temperature of a sample by 1 degree Celsius. It is the heat required to raise the temperature of a sample by 1 degree Celsius. And we label the heat capacity in units of joules per degree Celsius. So again, heat capacity is measured in joules per degree Celsius because again, that's the amount of heat. Heat is measured in units of joules, and temperature is in degrees Celsius, so again, joules per degree Celsius. Then we have another value that we're going to talk about here today, which is called the specific heat capacity. The specific heat capacity, and we abbreviate this with a C sub S. C sub S. And we define the specific heat capacity as being the heat required to raise the temperature of 1 gram of a sample by 1 degree Celsius. And so this is more specific. When we talk about the heat capacity, we're simply talking about the energy required to raise the temperature of a sample by 1 degree Celsius. More specifically, then we specify the amount of sample, which in this case would be 1 gram of sample, raising it by 1 degree Celsius. That means that in terms of units, we measure these in units of joules per gram dot degree Celsius. So again, the units on the specific heat capacity are joules per gram dot degree Celsius. Now, very often we abbreviate the specific heat capacity and simply refer to it as the specific heat. So again, specific heat is short for the specific heat capacity. And we often have tables then, as your textbook does, has tables here that list the specific heats for various substances. And so when we look at water, water has a value of 4.18, that's actually 4.184 joules per gram dot degree Celsius. And you may recall the demo that we did in here on Tuesday. We had the one where we took the hot copper samples, the hot copper cylinders, we placed them into the container water, and the temperature of the water rose. Now when we looked at it, we asked you to predict, in fact specifically, this was the example, we had 113 grams of copper at 99.4 degrees Celsius, we had 113 grams of water at 23.4 degrees Celsius. We placed the copper into the water, saw the temperature of the water rise, and we had to predict what that temperature would be. And most of us pick temperatures around 50 or 60 degrees Celsius. I think if I went back and looked at the most common answer, I think the most common answer was you sum the two values together and then you divide it by 2. Now, we described it a little bit at that time saying, well, yeah, that'd be great if each one of them had the same capacity to absorb heat, but they don't. What this is telling us, when we look at these specific heats, is that water has a greater capacity to absorb heat than does the copper. In fact, if we were to compare these values, the 4.18 to the copper at 0.385, tells us that water can take on much more energy per gram than can the copper. As a result then, the water, because it can take much more energy per gram, its temperature change is going to be relatively small. It's able to maintain a more constant temperature than copper. Copper is going to change temperature very quickly. And that's one of the reasons why, let's say if you were to go to a football game this time of year, they have metal bleachers or whatever, you sit on those metal bleachers and how do they feel? Well, they feel very cold because your body is mostly water. Your metal that you're sitting on has a low specific heat, and that is going to wind up transferring that heat into you very quickly because your body has the capability of taking on heat a lot more. Actually, your body will wind up losing the heat to the metal, but it's because your body has that much higher heat capacity than does the metal benches. So when we do these calculations right here, we look at what that relationship is between the specific heat and the heat capacity. We'd say that this is the relationship right here. We'd say that C, let's try it again here, C, I'll put it in a different color, C is equal to the mass times the specific heat capacity. So again, this value C right here is equal to the mass times the specific heat capacity. So if we then take this original equation right here, Q is equal to C times delta T, we can go ahead and plug in the M times C delta, or C sub S into the equation, and we wind up with an equation that says Q is equal to M times C sub S times delta T. And so one of these two equations that I've boxed here in the red, one of these two is one of the types of equations that we will wind up using in our study of calorimetry. So if we were to look at an example, let's look at the one that we did here in class the other day. And what we worked on in class is we had the 113 grams of copper at the 99.4 degrees Celsius. We had the 113 grams of water at 23.4 degrees Celsius. We want to know what is the final temperature. So we figured out what that final temperature was experimentally the other day. Let's see if we can predict what that would be here theoretically. Now the calculations that you see here today are going to be the same types of calculations that you'll be doing in your thermochemistry lab next week. In fact, I think we have a test coming up next week, is that right? Yeah? Thursday? Okay. So whatever you see on your lab on Wednesday and what you see here today obviously is going to show up on your exam on Thursday next week. And so I would take your lab very seriously next week. Try to get all those calculations done, because what you see in that lab is going to be a whole lot of what you're going to see on your Thursday exam. And it's a repeat, of course, of some of the stuff we're doing here today. So from our Socrative app questions, we saw that the Q value for the system and the Q value of the surroundings, how are these related to each other once again? They're the inverse. Well, inverse, yeah. Meaning that we are going to change the sign. So we'd say that the Q value for the system is equal to the negative the Q value of the surroundings. In this case, we could say that the system is the copper. We could say that the Q value for the copper is equal to negative the Q value of the water, of H2O. So again, what this is saying is whatever heat is lost by the copper must have been gained by the water. And again, that's why the signs on here are negative. Now, if we were to look at some of our equations, we know that Q is equal to m times C sub s times delta T. And we know that delta T stands for, help me out here, change in temperature. More specifically, it's going to be the, is it temperature at the end or temperature at the beginning? What does delta mean? Right, T final minus T initial. Remember, delta always means to take the final state minus the initial state. So T sub F, let's just call it T sub F and T sub I, so we don't have to keep writing these out. Looks something like this. So now if we were to make a substitution in here, we would then have m times C sub s times delta T for the copper. This is going to be equal to negative m times C sub delta s delta T for the H2O. So again, all I've done here is I've substituted in m times C sub s times delta T in for the Q on each side. Again, these signs are going to be opposite of each other because Q value of the system is equal to the negative Q value for the surroundings. Well, at this point, we should be able to substitute in the values on each side. And let's go ahead and do that. On the copper side, this right here, what is the mass of the copper? 113 grams, exactly. So 113 grams. What is the specific heat capacity for the copper? Well, we come back here. And where you're going to find this, I forgot to write down the page number in your text, but you'll be using these here in your homework. For the copper, that value is 0.385. And again, that's units of joules per gram dot degrees Celsius. So we'll come back here and put in 0.385 joules per gram dot degrees Celsius. And then we'll have delta T for the copper. Delta T again is T sub F minus T sub I. We don't know what T sub F is. That's actually what we're trying to find. We're trying to find out what is T sub F. But we do know what the initial temperature of the copper is. And what is the initial temperature of the copper? 99.4 degrees Celsius, exactly. Okay, then we will set this equal to, on the other side for the water, what is the mass of the water? 113 grams. There we go. And we can't forget this negative sign. That's probably the number one mistake here in our thermochemistry, is to forget the signs. Then we're going to take times the specific heat capacity of the water. Right up here we find that it's 4.18 joules per degree Celsius. 4.18 joules per gram dot degree Celsius. Then the delta T for the water is going to be T final minus T initial. Now, of course, we don't know what the final temperature is, but we do know that the final temperature of the copper and the water should be the same. Because again, the water is going to gain in temperature, the copper is going to lower its temperature. So the initial temperature of the water we'd put in would be 23.4 degrees Celsius. Now, I don't know about you, but for me, when I start looking at all these units in here, I don't like to deal with that in mathematics. So what I'm using units for at this point is just to remind me, what are the units going to be on T sub F once we calculate it? Degrees Celsius, exactly. So what I'm going to do then is, in the next step, is to cancel out some units. Oh, not quite yet. I want to cancel what's common to each side. If I want to simplify this, what can I divide each side by?
113 grams.
Exactly, 113 grams on each side. So if I take each side, divide this by 113 grams, that gets rid of this. And then this winds up being a simple algebra problem. So we'll distribute the 0.385 across parentheses, and again, I'm going to drop units off at this point because I've already confirmed what the units must be. I'll take the 0.385 times T sub F. That's going to be minus. And then we'll take the 0.385, 0.385, and we'll multiply it by the 99.4. And we do that, we wind up with 38.269. Right now I'm not going to worry about dropping any digits. We'll worry about that on our final answer. Then on the opposite side, we're going to have a negative. We'll then have a negative 4.18 T sub F. And then we'll take the 4.18. We'll multiply that by 23.4. And we get 97.812. Now the sign here, is this going to be a plus or a minus?
Plus.
And why is it a plus?
Because it was initially negative and then you gotta convert.
Right, because we're taking a negative times a negative, and a negative times a negative is going to give us a positive. So this here is our equation. I don't like negative numbers, so I'm going to move the put the T sub F's on this side. We'll move this over here. So in other words, we will add 4.18 T sub F to each side. So we'll take 4.18 plus 0.385. You may do your algebra differently. We should wind up with the same result. But on this side, I'll get 4.565 T sub F. And then I'm going to add the 38.269 to each side. And on this side, I'll get 136.081. So again, we're just grouping like terms together. Then if we want to simplify this answer, what do we do to each side?
Divided by 4.565.
There we go. Divide by 4.565. 565. This is going to cancel out here. This will cancel out here. We'll take the 136.081. We'll divide it by 4.565. And we wind up with an answer of, and it looks like if our temperatures have been going out to the nearest tenth, we'll maintain that consistency. We'll take our answer out here to the nearest tenth. Taking it out to the nearest tenth, we wind up with an answer of 29.8. The label on this again would be degrees Celsius as our result. So we would have predicted a temperature of 29.8 degrees Celsius. If we go back to our results here the other day, our results, we came up with 29.2 degrees Celsius. So we were pretty close. We were about 0.6 off. Actually, that's probably the furthest off I've ever been in a actual compared to a theoretical when I've demoed this to the class. Any questions on this? Oh, that's even less off. No, we're right there. Because what was it? It was 29.8, yeah, to 29.2. Any questions though on the math? Okay, so again, the chemistry of this is actually the easy part. What people struggle with is the math part on this, and probably the biggest thing is the signs. Keep track of your signs, please. Don't flip a coin. Ask yourself what they mean, and that's the whole purpose of that Socrative app questions when we came in here today. Okay, any questions that you have? Okay, next up. This one here, we might ask, how might we calculate work done by a gas? How might we calculate work done by a gas? And so we're going to go back to our example again. Tell me in the syringe, In which scenario are we doing work? When I'm pressing down or when the plunger is pushing back up? When I'm pushing down or when the plunger is pushing itself back up? When the plunger is pushing itself up, then we say that the system is doing the work. And if the system is doing the work here when the plunger is going up, how does the final volume compare to the initial volume? Okay, watch again. When the system is doing work, again, the system is doing work in this scenario right here. Is the final volume greater than or less than the initial volume?
Less than.
Let's do it again. The system is doing work when? When is it doing work? When I let go, right? And when I let go, what's happening to the volume? It's increasing. So the final volume at the end is greater than the initial volume when the system is doing work. Okay? So if that's when it's doing work, let's go back and do the math here of this and go back to our physics equation, which says work is done whenever we apply a force across a distance. And so our equation the other day says that work is done when we apply the force across a distance. In other words, work is equal to F times D. Now, back when we were dealing with gas pressures in here, we say that a pressure exerted whenever we look at the force per unit of area. So again, this is when we were looking at our gas laws. We said that the pressure is defined as being the force per unit of area. Now what I want to do is I want to make a substitution in here for the variable f. If I'm going to make a substitution in for the variable of f, I need to rearrange this equation here and solve for f. So if I rearrange this and solve for f, I want to get f by itself. So to get f by itself, I have to take each side and multiply by a, by the area. So we get rid of this and we find out that the force is equal to the area times the pressure. We then make that substitution in here for the force. And when we do that, we find out that the pressure times the area times the distance is equal to the work. Okay? Now, what we can look at here is that the distance traveled, if I go back to the syringe, so again, the system is doing work when I release this plunger. It's going up here. And when it goes up here, we're saying that this plunger is changing in height. It started from a lower height, it's winding up with a greater height. And so this distance that it moves, we could say is the change in height. And this plunger that's in here, this has an area that's in this space that remains to be the area, and so we'd have the pressure times that area, which remains constant, and it's the height of that cylinder that changes. Well, if we look at what area times height means, or area times distance, we wind up with a three-dimensional value, which is going to be volume. Okay? Because if you take the area of the base, and this is true of any three-dimensional object, if you take the area of the base times its height, you will wind up with the volume. Because volume is length times width, not volume. Area is length times width, and volume is length times width times height. And so again, it's the area of the base times the height. So this here winds up being essentially the change in volume. So again, the work is equal to pressure times the change in volume. Now again, we said that the volume, delta V, is equal to the final volume minus the initial volume. And we said that this final volume, when the system is doing work, when the system does work, then what happens is that the final volume is larger than the initial volume. And if the final volume is larger than the initial volume, that means that the sign on delta V is going to be a positive value. Okay, now because it's a positive value, if we go back to our sign conventions, our sign convention says that work is done by the system when the sign is negative. Okay, so what that means then is I'm going to throw in a negative sign into here, and that negative sign is to maintain the sign convention. So again, this negative sign is placed in here. We multiply by a -1 to maintain the sign convention for work being done by the system. And so we don't just throw it in there for a reason because the signs don't match up. The reason why we throw it in, well, it is in part because the signs don't match up, but the reason why the signs don't match up is, again, when work is done by the system, the sign on W must be negative, whereas the change in volume is a positive value, and the two signs then must be opposite. So this is one of those relationships, then, again, I'm trying to box the ones in red that we'll be using, is that work is equal to -P times delta V. Well, if we go back then and look at one of our other statements here from Tuesday, and I think this was probably right near the end. Let's see, trying to remember where we came up with this one. Here we go. No, not here. Oh, did we not do this one yet? Trying to find where we looked at this one the other day. Somewhere in here. Did I not put this in? Well, darn it. Was it at the very beginning? I don't remember where we have this. Again, I'm losing track of my two classes. Oh, here we go. Well, I guess we didn't write it out altogether. But what we say is that the internal energy is the sum of the kinetic energies of a substance, sum of the kinetic and potential energies of a substance. And somewhere I thought, I could have swore, we had written an equation out that says, and this must just be in my imagination, that delta E is equal to Q plus W. Gosh, we had to have done that somewhere. But again, the total internal energy is equal to the heat of the system plus the work done by the system. And I'm not seeing that anywhere. But when we look at this then, if we want to find out what delta E is equal to, what we're going to do is that we want to find out what the delta E is, or the change in internal energy for the reaction. We are going to assume a constant volume. And we assume a constant volume, or constant V, we'll give a label of Q sub V plus W sub V. And what we're trying to do is we're showing one of the ways we can simplify this process. So we're going to assume a constant volume. Well, if we assume a constant volume in this particular reaction, if V is constant, what is delta V equal to? 0. Because again, if the volume is constant, again, this is equal, delta V is equal to 0. If this is equal to 0, 0 times any number is equal to 0. 0 times any number is equal to 0. What that winds up telling us is that the change in internal energy for a reaction is equal to Q sub V. Again, that's because, in this case here, this winds up equaling a value of 0 because the change in volume is equal to 0. And so we'll wind up with a simplified version of this as a way to calculate the internal energy of a reaction. So we're going to apply this here now in some examples, and you'll also be applying this in your lab next week. To apply this, let's go ahead and look at an example. And this is in your packet now. We have a few problems that we're going to be going through here today, and we'll bring this with on Tuesday, how we can do some simplifications. And this is an activity or a device called a bomb calorimeter. And bomb calorimeter is something that we can use to look at the nutritional value of foods. We also look at it to determine their standardized values for the enthalpies of reactions that are published in books or now on websites. But this is a device called a bomb calorimeter that is used to measure energy contents of foods. And I brought one such example out here. And here's the construction of what that is. This here is an insulated container. You'll see the thick walls. And inside of here, we have a steel container called a bomb. Okay? Now, if I open this up, you'll notice that we have a lot of threads here, and this metal is very thick on this device. Open up the bomb. On the inside here, we have a little sample cup. And if we were, say, determining the energy content of foods, what we do is we would go ahead and grind up whatever sample it is we're working with. We'd place that sample into this metal cup here, and then we run an extremely thin wire between each of these two. These are electrodes that ultimately, on the outside here, wind up getting plugged into an igniter. Okay, and that runs some electricity onto the inside of this, into the top of this device, that when we run the electricity through there, that wire heats up. Once it heats up, it will cause the sample to burn. And when it burns, then it's going to give off heat. Now, to actually make it react, what we do is we place the sample into here, we place it back in, we seal the bomb up real tight, and we hook it up to some pure oxygen right here. This is a connector to a gas supply. We hook it up to a supply of pure oxygen, and we add the oxygen to a pressure of about 25 to 30 atmospheres. So not only is it pure oxygen, which makes things burn rapidly, we put it at a super high pressure so that the oxygen molecules are super crowded together and make sure that it reacts thoroughly. So again, once we ignite it, then what will happen is that there's going to be a small explosion that with high pressure and the reaction taking place, there'll be an explosion. That's why we have the thick-walled container. Even a cereal sample is going to explode at that high pressure and temperature. And so then, of course, it's going to give off heat. Once it gives off heat, this is sitting inside of this container. This container is going to contain some water. And then inside of here, there's a device which is hooked up to a belt. This is a motor here. This spins us around. What do you suppose this does? Well, this is sitting inside of here like this. And so as this sits around here, what do you suppose this is doing? It's mixing up the water that's inside of here. So we do that to get that temperature of the water to be uniform throughout, and that's why we have the little propellers that sit on there. And then it sits inside of this, so it's all insulated. Now, this is one of those things, I know you talked about your lab projects yesterday, but if looking at this device makes you think you might want to modify whatever lab project you may have selected, you can do that. Again, here's what that bomb calorimeter winds up looking like. And so at the end, it winds up not actually being that exciting, because again, on the outside here, you press a little igniter button. That igniter button will send electrical current through these wires into the bomb. You'll have the explosion, and the temperature goes up. So what we're reading here then is an example of what happens when we're using the bomb calorimeter. And it says that when we place the hexane into here, so we would have placed the hexane into our sample cup, we've ignited it, which means it goes through combustion of the bomb calorimeter. The temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. And we'd then like to find the total internal energy change for the reaction in kilojoules per mole of hexane. And it says that the heat capacity of the bomb calorimeter, determined in a separate experiment, is 5.73 kilojoules per degree Celsius. So we'd go through, what I like doing when I do this is I like labeling all the different things. So I'm going to label this that C, which again is the heat capacity, is equal to how much? Well, if we read through this, what is the heat capacity of this calorimeter? 5.73 kilojoules per degree Celsius. Then, the water itself, this goes through a temperature change. We have the final temperature, we have the initial temperature. What is the final temperature of the water? 38.13 degrees Celsius. Its initial temperature was 25.87 degrees Celsius. And so at this point, we should be able to find out what the heat is for the surroundings. That is, the Q value of the surroundings is equal to C times delta T. We then place the value into here. C is 5.73 kilojoules per degree Celsius. We then multiply that by delta T. Delta T in this case is going to be final minus initial. So what is delta T equal to? We'll subtract the two from each other. And what do we get? 12.26. The label would be degrees Celsius. And this is a positive or negative delta T. It's going to be positive delta T. So it'll be a positive 12.26 degrees Celsius. Units of degrees Celsius are going to cancel out. And that tells us that the Q value is going to be equal to 5.73 times 12.26. It will wind up having a value of, and we'll carry along a couple extra digits. Looks like this would have a value of 70.250. And the label is going to be kilojoules. And of course, this would really only be good out to 3 significant figures. But we'll carry along a couple of extra digits for right now. Now, of course, this is the Q value for the calorimeter. Remember, the calorimeter is a part of the surroundings. We don't want to know what is the Q value for the surroundings. We want to know what is the Q value for the system. So we then remember that the Q value for the system is equal to negative the Q value of the surroundings. And we just saw on our previous calculation that the enthalpy of reaction is equal to the Q value of the system. So we can then say that this is equal to 70.250 kilojoules. But the sign on the system here, what is the sign going to be? The sign on here is going to be negative, because the Q value for the system must equal the negative of the Q value of the surroundings. The calorimeter is part of the surroundings. We want to figure out what the value is for the system. So again, this sign on here is negative because the system and surroundings must have opposite values. Well, then we can take that negative 70.250 kilojoules, which is the amount of energy that is released, and this is the amount of energy that is released for every 1.550 grams of the hexane. And if I zoom out here, looks like I need to zoom out a little bit more. Here we go. We have the 1.550 grams of hexane. So that was the energy released for every 1.55 grams of the liquid hexane. What we want to do is we wanted to find the delta E in units of kilojoules per mole. Not the number of kilojoules per 1.5 grams, but the number of kilojoules per mole. So if we came out here, we want to know the number of kilojoules for every mole of the hexane. What do we need to do? What do we need to do to get to units of kilojoules per mole?
Molar mass.
Molar mass, exactly. So in our molar mass, on the top we're going to have units of grams of hexane. On the bottom we would have units of moles of hexane. And of course the molar mass is always the grams contained in 1 mole. So if we then go to hexane and calculate that molar mass, we have 6 carbons, we have 14 hydrogens. So we'll have 72 plus 14, which is about 86. More specifically, it's going to be 86.17. Good. There's the number of grams for every mole. At this point then, the grams of the hexane are going to cancel out. We'll take the 70.250, we'll divide it by 1.55, multiply by 86.17, and we wind up with an answer of a negative 3905 kilojoules per mole of the C6H14. Of course, now we said that this value here really only has 3 significant figures, which means that our answer here should only have 3 significant figures. If we round this off to 3 significant figures, we would then say that our answer is going to be a negative 3.91 times 10 to the negative third, because we'll move it 1, 2, 3 places. The label then would be kilojoules per mole of the hexane. And so typically when we standardize these enthalpies of reaction, we are going to be standardizing them and labeling them in units of kilojoules per mole. All right, what questions do you have on this? What questions do you have? Well, let's look at another one then. We're going to look at another value called enthalpy. Enthalpy. And enthalpy is designated by the capital letter H. And don't ask me how chemists originally designated these variables. To me, H sounds like it's heat, and actually we'll find out that enthalpy and heat are very closely associated anyhow. But we define enthalpy like this. We define enthalpy as being a state function that equals the sum of the internal energy which of course is E, and the product of pressure and volume. So it's a state function that equals the sum of the internal energy and the product of the pressure and volume, which we say is PV. Product means that we're going to multiply them together. And remember that when we talk about a state function, all that matters in the state function is the final state and the initial state. The way you get there doesn't matter. So only the initial state or the final state is what matters. We also say that enthalpy is an extensive property, which means that the amount matters. So again, it's also an extensive property, which means that the amount matters. The more of it we have, the larger the value is going to be. So we talked about if we burn a larger piece of wood, or burn more gasoline, we have a larger enthalpy value, which is one of the reasons why we go back and always standardize it in terms of an amount per mole. So if we were to put in the symbols what this means, that means that H is equal to E plus PV. That's what this definition means. But as we are going to find out, we want to look at these and apply them to chemical reactions. So we are going to look at the change in enthalpy. We'd say that the change in enthalpy, and this would be for a reaction, is equal to the change in internal energy plus P times delta V. Well, now if we look at where this comes from on here, we could take this a step further, and we remember that just earlier today we said that the amount of work done by the system is equal to negative P times delta V. And we also said that E, or the delta E, is equal to Q plus W. So if we make this substitution right here, we could put in for delta E a Q plus W. So putting it in there, we're going to get a Q plus W. And then over here, we can say that W is equal to, I'll put this in a different color, W is equal to negative P times delta V. In other words, if we were to kind of manipulate this just a bit, we could say that negative W is equal to P times delta V. We can then substitute in a negative W for P times delta V. So if we substitute in a negative W, what we find then is that the change in enthalpy for a reaction is equal to Q plus W minus W, and this will take place when we are at a constant pressure. And so at a constant pressure, we could then say that the enthalpy of reaction is equal to, a change in enthalpy of reaction is equal to the Q value at a constant pressure. Now, in most cases, what we're going to find out is that in most cases, the change in total energy of a reaction is going to be very close to the change in enthalpy for a reaction. Or they're going to be about equal. They're going to be further apart when we have large values of delta V, when we have large volume changes. Like if we have an explosion which produces a gas, then we're going to have large delta V's. But in most cases, whether we calculate a change in enthalpy or a change in total energy, those values are going to be about the same in terms of numeric values. So what this leads us to at this point is our ability to look at chemical reactions. And so we can then look at a chemical reaction and talk about the enthalpy change for those reactions. When we write out a chemical equation like this is what we call a thermochemical equation. This here is called a thermochemical equation. And a thermochemical equation is a balanced chemical equation which also has the enthalpy, change in enthalpy associated with that reaction. And the assumption is this, the assumption is that these coefficients stand for units of moles. So and when we write out this chemical equation as a thermochemical equation, the assumption is that these coefficients stand for moles, and this here is the energy associated with this chemical equation in terms of units of moles. When we see a negative sign on here, this tells us that this reaction is an exothermic reaction. If the sign on here is positive, that tells us it is an endothermic reaction. So again, think about these when we defined the signs and looked at the sign conventions before. A negative sign means energy out. A positive sign means energy in. So this means we're taking energy out of the system. The system is releasing it to the surroundings. So in this case here, if we were trying to find out how much heat is given off, we could say to calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So here's how we go about doing that. We're going to start off with what we're given. And what we're given here is 155 grams of NH3. And we want to calculate the heat in units of kilojoules out here in the answer. So now this actually winds up being very much a stoichiometry problem. We're going to take the grams of ammonia, and to use the thermochemical equation, we need to take the grams of ammonia and convert it into moles. We need to convert grams into moles. So to convert grams into moles, we'd put grams in the bottom, and the top would put in moles. Now how do we get the number of grams down here? The molar mass, exactly. So if we want to do the molar mass, we come back to the periodic table. We'll look up the mass of nitrogen and 3 hydrogens. So 1 nitrogen plus 3 hydrogens is going to give us 17.03. And that's going to be the number of grams contained in 1 mole. Grams of NH3 are going to cancel out. Now we have moles of NH3. We want to get over to kilojoules. So in this case then, we want to place on the bottom moles of NH3, and on the top we want to place in kilojoules. And now we're going to treat this value just as if it were a coefficient. And we would say that we have negative 906 kilojoules for how many moles?
4.
Exactly. So again, we take this number here, the 906, relate it to the 4 over here. The units of moles are going to cancel out. We go ahead and do this math. We'll then take 155, we'll divide it by 17.03, we'll multiply by negative 906, and we'll divide this by 4. And upon doing so, we wind up with an answer of, looks like it's going to be 3 significant figures, but we'll write it out here first as negative 2062 kilojoules. And of course, if we want to place this then as 3 significant figures, we would write this answer as being a negative 2.06 10 to the third. And did I put a wrong label? I'm just now thinking.
Yeah.
Did I? Yeah. So it's times 10 to the positive third on this one. And now I'm realizing, gosh, I'm stupid. Back here this wasn't, I think I said a negative 3. And this must have been a positive 3. If you discover that mistake, by all means, please correct when we do that. This back here is a positive 3. And this is even where I get, it's not mixed up. I let myself think of this negative sign out here as influencing the exponent. It doesn't. And so it is a common mistake, but it's a mistake you don't want to make, like I just made, all right? Because it's a huge, that's a factor of 1 million that we have on our answer. So this is times 10 to the positive 3 on the kilojoules. Okay? Now, here's an alternative wording. And here's the part that, again, a lot of people, what we're doing, this is not difficult stuff. The biggest thing is going to be signs. We learn very little in this chapter. most of what you are going to be doing this chapter is stuff that we've already done. We've done stoichiometry before. This is nothing new. We're just adding on one more term in a balanced chemical equation. So we didn't introduce anything new on this here. The biggest thing is that keeping track of your signs, just like you saw me make a mistake on the signs on the exponent. So this one here, let's interpret, before we look at the alternative wording, let's interpret. What does the negative sign mean? What does the negative sign mean in this particular one? If we say that this is the heat, and the heat is negative, what does that mean?
It's giving off.
Right, it means that it's giving off heat. That's what it means. It means that we're releasing heat. It means that we are producing heat. Okay? So now, if the alternative wording is this, and I'll circle this in, say, in orange, if the alternative wording is this right here, it says how much energy is produced, we would say that 2.06 times 10 to the positive third kilojoules were produced. Okay, so this is the interpretation that we would have for this particular problem. So tell us that we have 2.06 times 10 to the third kilojoules that were produced. The negative sign tells us that energy was produced. And we can't produce negative amounts of energy, all right? So if the question was, and this is why you need to pay attention to wording. This is how I might word it on the exam. If the question was how much energy is produced and you put in a negative sign, again, you can't produce negative energy. You're going to be producing positive amounts of energy. So the sign in there tells us, this negative sign here tells us that energy was produced. Okay, any questions with that one? Okay, finally, I think this is probably where we will end for the day. Well, we might get in a little bit further. Let's look at these this thermochemical equation right here. And given this reaction, let's give these values in these blanks. Now, if we look at these particular values that are in here, let's look at this equation right here compared to this one. How does this equation compare to the first one?
It's just doubled.
It's just double. So if we double the size of the coefficients, what do you think we should do here?
Double.
Double it as well. That's it. It's that simple. Let's look at this equation and then look at this one. How do the coefficients in this equation compare to this one here? It's half. So what do you suppose we do to delta H? Cut it in half, exactly. So to cut it in half, 46 divided by 2 is? Right, so it's going to need to be a negative 23 kilojoules. Look at this reaction right here. How does it compare to what we're given? It is flipped around. If we reverse the reaction direction, what do you think happens here? It becomes positive. We simply change the sign. So this here becomes a positive 46 kilojoules. Okay? So this is how thermochemical equations work. When we change the direction of the reaction, we change the sign. If we change the size of the coefficients, the sign on delta, or the size of delta H, changes proportionately. So this takes us to what we call Hess's law of heat summation. And Hess's law of heat summation is worded like this. In fact, if you look at your lab for next week, your lab next week is Hess's law of heat summation. It says that the enthalpy change delta H for a stepwise process is equal to the sum of the enthalpy changes that comprise the steps. So if we look at a stepwise process, the enthalpy change for a stepwise process is equal to the sum of the enthalpy changes that comprise the steps. Now this works just like if we were summing together algebraic equations. If we had something like this, 2x plus 5y is equal to 8, and we added to this 3x minus 8y is equal to negative 13. If we sum these two equations together, what are we going to get? Right, this is what we wind up with. If we sum these equations together. Chemical equations work just like algebra. Okay, we sum down. So that takes us to our next problem in our packet. And so our next equation in the packet here, next problem, says that we want to calculate the enthalpy change for this reaction. In other words, we want to know what is this value equal to. That's the problem. We want to know what is this value equal to when we know these three values. Okay, so what we're going to do is we're going to manipulate these three equations so that they sum together to give the one up above. So we need to manipulate these three equations. So now to manipulate them, let's take equation number 1, and we're going to manipulate this one here. Now, but to manipulate this one, I am looking at the equation we're trying to solve for. We see that CO2 is on the product side. In this one here, we see that CO2 is on the product side. But what's the difference between these two equations? Well, I mean, a lot of difference in the equations, but what's the difference between the CO2 in these two equations? This one here has a coefficient of 4. This one here does not have a coefficient of 4. So if we want these two equations to sum together, we're going to take this first equation and we're going to multiply it by a factor of 4. So if we distribute that 4 across the parentheses, let's distribute that 4 across the parentheses. We'll take a 4 here, we'll put a 4 here, we'll put a 4 here. If we put a 4 here, that means we're going to take this value here and we're going to multiply it by a factor of 4. And so taking equation number 1, it would say that we have 4 carbon solid plus 4 O2 gas yields 4 CO2 gas. We take 4 times a negative 393.5. We're going to get a negative
1,564.
I have 74. Is that wrong?
No, I might be wrong.
Well, I could be wrong. Got to check mine. 74? Yeah, 74 is what we're going to get.
Oh yeah, I did that wrong.
Yeah. The label on this is going to be kilojoules, and the sign again is going to be negative. So then, we take the next equation. We want to manipulate equation number 2. This one here, we see that C2H2 is on the product side. In the given reaction, the C2H2 is on the reactant side. So what do you suppose we need to do to equation number 2? Multiply by 2. And what else do we have to do? We need to take that equation and flip it around. So I'm going to take this equation right here and I'm going to multiply it by a negative 2. Remember the first one we multiplied by a positive 4, but the second one we're going to multiply by a negative 2. When we multiply by a negative 2, again that flips the equation around. When it flips it around, we get a 2 C2H2 gas yields, And now it's not going to be 2 carbons, it's going to be 4 carbons plus 2 H2 gas. So again, what I've done is I've taken this equation and I've flipped it around. And the reason why I flipped it around is that I want these equations to sum together to get the C2H2 on this side. And why again did I multiply by a factor of 2? Because the coefficient in here is equal to 2. So here the coefficient's a 1. If it's equal to 2, that means I need the equation to be 2 times as big. So if I flip the equation around and multiply it by 2, that means I need to take the delta H and multiply it by a negative 2. The delta H for this equation is equal to negative 2 times this, which would be negative 453.4. And that would be in units of kilojoules. We might go over a minute or two here, I apologize. Finally, if we look at our last equation, we see that H2O is in this equation. H2O is on the product side. Over here, H2O is on the product side as well. Here the coefficient is a 2, here it's a 2. So what do you suppose we do with this last equation? We just leave it, exactly. So we write out equation number 3 just as is. So it tells us that 2 moles of hydrogen gas plus 1 mole of oxygen gas yields 2 moles of H2O in the gaseous phase. The enthalpy change is equal to negative 483.7 kilojoules. Well, now if we take these equations right here and sum them together, let's add these equations together at this point. If we sum them together, looks like we have 2 moles of C2H2 on this side, 2 moles of C2H2 on this side, gas. How many moles of oxygen gas do we have all together on this side here? We have 5 moles. So we're going to sum these together and we're going to have 5 moles of O2 gas. What happens to the H2? We have 2 moles of H2 on the left, 2 moles of H2 on the right. What's going to happen to that? They will cancel out, exactly. Again, this is an algebraic equation. They cancel out. We have 4 moles of carbon on the left, 4 moles of carbon on the right. What happens to them? They're going to cancel out as well. So then on the product side, looks like we have 4 moles of carbon dioxide gas. And it looks like we have 2 moles of H2O in the gaseous phase. And so again, when we sum the equations together, this is what we wind up with. Everything else cancels out. And so if the equations sum together to yield this value, we should then be able to sum together these values. So we'll take a negative 1574, add to it a negative 453.4, and add to that a negative 483.7. We wind up getting a value of, and I think I did something wrong here. I did. Okay. We end up getting a value of negative 2,511. The label on this is going to be kilojoules. And that means that the enthalpy change for this reaction is a negative 2,511 kilojoules. That then is what we place up here as the enthalpy change for this reaction is negative 2,511 kilojoules. Now I understand we probably did this without full explanation on it, but again, the idea is to manipulate these equations so they sum to yield the equation up above here, which it does. All right, digest this over the long weekend. We'll have to answer questions when we come back on Tuesday. I can't believe it's not